locking protocol is a set of rules for transactions to ensure safe interleaving in schedules. A schedule S is legal under a locking protocol if it can be generated by a set of transactions that follow the rules of that locking protocol. A protocol ensures serializability if all of the legal schedules generated under that protocol are serializable. A famous, widely used, and restrictive locking protocol is a strict two-phase locking. Strict two-phase locking has two rules. First, if a transaction T wants to read an object, it first requests a shared lock on the object. The rule is a little different for modifying, saying if a transaction T wants to modify an object, it first requests an exclusive lock on the object. The second rule says that all locks held by a transaction are released when the transaction is completed. The strict two-phase locking, especially with the second condition, can limit usage of some interleaved schedules because it dictates the order of what should happen in and between the transactions. We show a shared lock on object O by transaction T as ST of O, and an exclusive lock on object O by transaction T as XT of O. For example, in the given schedule, transactions T1 and T2 are interleaved. To gain access to read A, T1 first puts a shared lock on it. When later T2 needs to read A as well, since the lock is a shared lock, T2 can do that as well. Then T2 needs to read and write B. In order to be able to write, it needs to put an exclusive lock on it, and therefore no other transaction can gain access to it afterwards. The same for resource C, an exclusive lock from T1. The locks are released when the transactions are completed, which means after the commits. The compatibility matrix for locks is depicted in the shown table. It shows that shared locks can be gained access to by other shared locks, but no other combination is possible. That is why, in our example schedule, T2 was able to get a shared lock on A once T1 had a shared lock on it. But if there was a need to write on A at the same point, it could not get an exclusive lock. That is, due to compatibility with the prior lock on the object. This is, of course, for strict two-phase locking, and relaxations are considered in different variations of the protocol. There are different versions of two-phase locking protocol relaxing the strict two-phase locking in different ways, including a version that only needs keeping exclusive locks until end of the transactions, and the version which enables lock conversions to upgrade locks to exclusive and downgrade them to shared in specific conditions. However, the most important and most well-known variation, which simply is called two-phase locking, is known for relaxing the second condition in strict two-phase locking. The relaxed condition states that a transition cannot request additional locks once it releases any lock. The simple assumption implies that each transaction has a growing phase in which it acquires locks, and since it cannot request additional locks after it releases any lock, it will go into a shrinking phase. Following this definition of second rule and the phases of growing and shrinking, it can be proven that two-phase locking produces acyclic precedence graphs and therefore produces only conflict serializable schedules. The additional condition in strict two-phase locking, which was ensuring the release of the locks at the commit or abort, additionally ensures the recoverability of the schedules, which is not available in the simple two-phase locking.